Hello, Physics 2. Let us continue in Chapter 22, building on Faraday's Law. So now we're going to connect Faraday's Law to motional EMF, which that little example we did at the beginning of this chapter should have given a giant hint that this was coming in your direction. So we learned about motional EMF in Chapter 20. Which is essentially you move a wire or a conductor through a magnetic field and you can make a circuit. Where that motional EMF is essentially acting like the battery in your little circuit. And equationally, motional EMF for a bar or for a wire or a bar of length capital L, we can write it as EMF is equal to Q V cross B L over Q, where V is the velocity of the bar. So, and then I'm also going to note just another quick recall, because you may occasionally see me use this terminology if I'm writing a solution out for you, although I'll try to keep it out of the notes. The symbol for EMF is also that curly E, and that is actually the more common symbol. So I'm more telling you so that if you see this in another book, you know that these are one and the same. Within our notes, I'm going to be sticking with EMF because that's what we agreed upon. But if I do a quick solution for you, I might use that curly E. All right, so moving on. So end that recall. So if the velocity is perpendicular, so let's use red for velocity, to our magnetic field, so let's say the magnetic field here is pointing down, so we've got velocity perpendicular to B, then EMF is equal to VBL. All right, so that brings us to where we left off in Chapter 20. So we can calculate motional EMF in terms of magnetic flux. So let's build our little picture again. Get some pretty colors going. So we've got our resistance right here, and we've got our little, let's just leave this all in blue. Okay, so we've got our bars right here. We've got our magnetic field. I'm feeling orange for magnetic fields today. Blue and orange, like superhero colors. All right, so there we go, magnetic field going in. And then we've got our bar here, which is moving and conducting of some length. Okay, so this is going to move some distance v delta t in some delta t. So the bar moves delta x is equal to v delta t. And in this case, when it moves some v delta t, what happens is the area of the circuit is also increasing. So when delta x non-zero, then delta A, let's try that again. Delta A is equal to L delta x, which is equal to L V delta t. Okay, so we have this increase of area. This movement also means the magnetic flux is increasing. So the change of magnetic flux is equal to B perpendicular delta A, which is equal to B LV delta T. And to get the change in flux, with respect to time, we can just divide both sides by delta T. So we divide both sides by delta T. And so you get delta flux over delta T is equal to B LV. And if we recall from earlier in the chapter, the change in magnetic flux with respect to time is equal to EMF. And so all of this goes to say that the magnitude of the EMF is equal to BLV is equal to the change in magnetic flux with respect to time. And the sign is given by the direction of magnetic force. So not the direction of the magnetic field, the direction of the magnetic force. So all right, so this is a general result. It also works for situations including a rotating wire in a field. It's strange to do this type of lecture because I feel the need to give you more in writing than I would in class, where I could talk to you a little bit just to kind of check in on y'all with me. Good. I figure if I just write a little bit more, then I can just give you that time where I would check in. Okay, so including a rotating wire in a magnetic field. So for example, we go back to that square circuit that we've seen before. We've got our B field. Let's see, so this is going to have our width, and we're going to have H here. This is rotating with some omega, and every year I'm like, I should change the W so it doesn't look like an omega, and every year I don't do that. You've got a normal unit vector, which is normal to the plane of this rotating square wire, and then you have the angle theta between them. So theta is equal to, right over here, theta is equal to omega t. You also have theta right here. And then, of course, this is all rotating in some magnetic field. Okay, so I'll write out a few things. And this is also inducing a motional EMF. So you're moving through a magnetic field, inducing an EMF. So n hat is at an angle with theta. Theta is equal to omega t to the B field. And the magnetic flux is equal to BHW cosine omega t. I know W and omega, these are two different things. And so EMF is equal to the change in magnetic flux divided by dt is equal to BHW sine omega t. So this is the same result as we got in chapter 20. We just looked at it from a motional EMF point of view. So this is one of the important things to do as you progress within the field of physics is when you learn a new method to do something that you already know how to do, you should get back what you've previously done. So, and the ability to think like that's actually useful not just within the field of physics, but really any analytical field. Okay, so there are two pieces of the time-based derivative for flux. So at this point, we know as soon as I say that there's a changing magnetic field, we know this results in a curly non-Coulomb electric field. So we have that down. Further, we have looked at how the change in magnetic flux with respect to time drives a current. So we know this too. And we also know, even further, that the change in magnetic flux with respect to time can be non-zero if the magnetic field is changing or if the shape is changing. So in the case of motional EMF, the shape was changing. So in both cases, you were able to have a change in magnetic flux. One was related to the changing of magnetic field, and one was related to the change of shape within a magnetic field. And both changes produce EMF. Okay, so, and just like the momentum principle, we can break this into parts. So, 2 parts to be precise. Okay, so we're going to look at the 2 changes, the change of magnetic field and the change in area. As long as one of those are changing, then you'll have a change of magnetic flux. Of course, both of them changing also causes a change in magnetic flux. Okay, so we have the change of magnetic flux with respect to time is equal to the change with respect to time of B perpendicular and A. This is equal to dB dt times A. It's a terrible A, but you get the point. That's where A is held constant, B is allowed to change, and B perpendicular, dA dt. So in this case, B is held constant, A is allowed to change. And so this is, of course, Faraday. And this is motional EMF. And so this is going to relate to a change in field. And this is a change in area or shape. Okay, so we can look at this from a motional EMF perspective. So d phi dt is equal to B perpendicular dt times A. I'm having some real issues with those A's, my goodness. Plus B perpendicular dA dt is equal to dB perpendicular dt, got it, A plus B perpendicular L dx dt. So now we're just plugging in what dA is, and this is equal to dB perpendicular dTA plus B perpendicular LV, which we've seen before. Okay, and just something to note, these changes can also occur by a change in reference frame. Remember, the eye of the beholder is important when it comes to making measurements. All right, so just wanted to recap curly NC and force. So if dB dt is not 0, then you'll have a curly non-Coulomb electric force around the change of magnetic flux. And from here you have EMF is equal to ENC dot dL is not equal to 0. Okay, so you can have 3 kinds of electric and magnetic forces on the electrons in a wire. So 1, you can have a Coulomb force from the Coulomb electric field from charges on the surface. All about chapter 18. And we get superposition. E is equal to 1 over 4 pi epsilon naught Q over R squared times R hat. So basically everything we did earlier on in physics 2. And you can have forces from the non-Coulomb electric field associated with a changing magnetic field. And you can have forces from magnetism, QV cross B, if the wire is moving. Due to a change in path. And all of these things can exist simultaneously or individually. So you could have all three forces, you could have two of them, you could have one of them. So it's important to read your setups carefully to know what you're dealing with. Okay, so we are ready once again to start or to continue our update of Maxwell's equations. Okay, so we've got E dot n hat dA is equal to 1 over epsilon naught times the sum of Q enclosed. So this is Gauss's law. We have B dot n hat dA is equal to 0, Gauss's law for magnets. We have E dot dl is equal to minus d dt B dot n hat dA, which is Faraday's law. And B dot dl is equal to mu naught times the sum of the current inside the path. And this is Ampere's law, and we have not completed it. So we had previously known 2. We now have 3, and we're still working towards number 4, and we'll get to number 4 in the next chapter. And as I said before, these are the foundational laws. They have been shown to hold through for more than a century of scientific tests. They are, in my opinion, the most important thing that you learn in Physics 2, that lay this incredible foundation for you to do so many more things in the field should you desire, or just to know something cool. And basically all of the laws that we have been discussing throughout the semester, like Biot-Savart and Coulomb, can all be derived from these laws. These are the most foundational. And so we will complete Maxwell's laws in the next chapter, and this wraps up part 1 of Monday's lecture.